So in this video, I'm going to be doing part 2 of this problem, and I'm going to use Python to simulate the dynamics of this controlled 3-tank system by solving our differential equations from part 1 using our SciPy integrate solve IGP. So to start off, I'm just going to import a few things. I'm going to import numpy as np, and then from plotly subplots import make subplots, and then I'm going to import this as well. So from SciPy integrate import solve IVP. And now I'm just going to enter in a few of the knowns from our problem. So first, the areas that it gives us. So our area 1, area 2, and area 3. And those are going to be equal to 0.5, 1, and 2. And then we also know the initial heights, which are going to be h naught 1, h naught 2, and h naught 3. And those are going to be equal to 0.5, 1, and 2 as well. And then our proportionality constant, Kc, equals 0.1. And our fluid level set point for the third tank will be 4 meters. I'll call that HSP3 will equal 4. And then also our alphas, our proportionality constants will equal 0.1. That's alpha 1, 2, alpha 2, 3, and alpha 3. And those will all equal 0.1. So now I'm going to define the function that we are going to use this solve IP for. So I'm going to define the function, and we're going to call it RHS for the right-hand side of these equations here are going to be what we will be returning. So define RHS, and we're going to be inputting our temperatures and heights. So temperature, and then our heights are just going to be a vector of the heights. So now we can define this vector as height, or we can unpack it as height 1, height 2, and height 3. We equal that vector. Now we are going to want to return our three equations from here. and that's going to be in an array. So our first one is negative Q12 over A1. And then our second one is Qn plus Q12 minus Q23 all over A2. And then the last one is Q23 minus Q out all over A3. And then now we are going to need to find our Q12, our Q23, our Q out, and our Q in. So Qn will be equal to our Kc times HSP3 minus our H3. And then Q12 will not be sine of H1 minus H2 times alpha 1, 2 times the absolute value of H1 minus H2, and that to 1/2 power. And Q23 will be the same thing, but with this as height 2, and height 3, and height 2, and height 3. And then finally our Q out will be alpha 3 times our height 3 to the 1/2 power. This is Q out. So now we are going to use our solve IVP to solve these differential equations. So solve IVP. And first it's going to ask us for our function, which is what we defined before as RHS. And then it's asking for a range of times. And I just want to clarify from before, this is our times here. I know I said temperature before, but this is supposed to be our change in times. So we can do like 0 to 200 seconds. And then it's asking for our initial heights as well, which we have from before. H0 1, H0 2, and H0 3. Then it's asking for our method, and the method that we're going to use is called Radu. And finally, for our dense output, we want that to be true. So as you can see, it gives us a bunch of numbers here. But what we're looking for is this sol portion here, which is basically just all of our solutions. So I'm going to put dot sol here. So now in order to plot this, we're going to need temperatures. Then I'm just going to call tplot to plot over. And we can just do linear space values for that from 0 to 200, because that's what we did here. And let's say about like 500 values. And then now we are also going to need to calculate our heights. So our height 1, height 2, height 3 at those temperatures. So I'm gonna make this equal to the variable sol. So now we can just call this over our tplot. To get our heights for plot. So now all we have to do is make a figure and add our plus to it. So our fig equals make subplots, and then we're going to add a scatter, and our x's are going to equal our tplot, our y's are going to equal h1. We'll set the mode equal to lines, and I'm going to name it our h1. And then we're going to do 3 of these. For each of the heights. And now I'm going to run all, just make sure that this works. And there we go. So just to kind of go over what this all means, I'm actually going to rename these by which tank they are. So this is tank 1, tank 2, and tank 3. And as you can see, let me enter this here. So our tank 1 starts around 0.5, which is what we entered up here. And our tank 2 starts around 1, which is what we entered here. And then tank 3 starts around 2, which was our initial height for tank 3 as well. So as you can see in the beginning, it fluctuates quite a bit as like tank 1 and tank 2 are going up. Right here in the beginning, tank 3 is going down. But then eventually, it even outs over here around like, I don't know, 150 seconds almost. It becomes steady state, and you're pretty much in a constant height at these points.